Hi, I'm Shawn Wigg, and this is a sample of excerpt number 4 for the video component of this interview, where we'll launch Eureka Math, a story of functions. This lesson will be about the coherence between a story of units, specifically, and a story of functions when it comes to the area model and tabular method. So let's start with doing a little bit of basic math. What I'd like each of you to do in the room is to take the numbers 15 and 13 and multiply them together. You'll do it without consulting your neighbor. You can do it in the method of your choice, but make sure you jot down your entire work from start to finish of how you multiplied 15 and 13. So let's take 60 seconds, do the math, and jot it down. Okay, now that we're done, how many of you did it through the standard algorithm? How many of you here? Good. Raise a show of hands. Show of hands. All right, a lot of us. Who did it differently? Someone walk me through how you did it differently. Good, yes. Very good. I like it. Very good. Another way. Anyone do it another way? No, just the two? Okay, great, excellent. What I want to do is show you the way that I did it, and let's take a look at that together. So this is my method. I'm not going to say a lot about it, because I want to know what you think about it. So what I'd like you to do at your table, we're going to do a turn and talk. Find your shoulder partner, and what I'd like you to do within the next 60 seconds is to discuss your thoughts on why you think I drew the model the way that I did, and why I may have chosen this method. So let's take about 60 seconds, share with your partner, and then we're going to share out. So turn and talk. Okay, so now we're done. Let's come back together. I heard a few things going around a little bit. Anyone have any thoughts to share? Let's do a share out here. Why do you think I drew the model the way that I did? Good. And maybe. Not going to give you the answer. There's no right or wrong one. How about over here? Anybody? Good thought. Maybe. Yeah, maybe so. Good. Those are all great ideas. I'm going to show you, but there's no right or wrong answer, but I'll show you why I chose it the way that I did. And let's see if by the end of today's session, you may choose this model as well. We'll see. All right, so let's take a look at this a little bit. Just for a refresher, in case you're not familiar with this particular grade band, this whole model is actually called the area model. So students use this to assist with multiplication. Inside of each one of these, we have something called the partial product. That's going to be important because I'm going to ask you some questions later about some of this so you'll know the vocabulary that I'm using, because there'll be a consistent use of vocabulary across the curriculum. This is the area model, and we have partial products that will exist within that area model. So when we think about how the curriculum is written in its beautiful tapestry of continuum and coherence across grade bands, I want you to think about the story of units. How do we connect that K-5 modeling to high school algebra? We've often said, oh, that's elementary, or oh, that's algebra. This is written in such a way that they can actually use some similar strategies. In that story of units, which is our K-5, students use that area model that I just showed to help them multiply multi-digit numbers. And what it does is it helps students actually understand multiplication algorithms. It gives them more than just factual memorization. It gives them multiplication understanding. What it also does is it clarifies the use of that distributive property, which we know is huge across mathematics. And it helps clarify that property to help them generate and record either 2, which is the sum of each layer, or 4, the sum of each area, partial products when they're multiplying two-digit numbers. So students are doing this regularly and consistently in the story of units to help build that foundation. So let's go back to the one that I did. What I'd like you to do on your participant handout, the Algebra 1 Module 1 task, you're going to see Part A. On part A, I would like you to see if you can complete the remaining portions of this model. If you're unfamiliar with the model, I'll help you with the first one, and I think you'll get the idea of how it actually works. So what we're going to do is we'll take this first number here of 10, multiply it by this number of 10 to give us our first partial product of 100. If you're unfamiliar, that's how it starts. If you can work with a partner on this one if you need to, but let's take about 2 minutes and let's fill in the remaining portions of this model in part A on your handout. Okay, looks like everyone's done, so let's bring it back together. Let's take a look at these. What did you get for your upper left-hand side of your area model? Good, and you got it from the 10 and 10. We talked about this one together, very good. What about your next one? Who can help me with the next one? Good, from the 5 and the 10, perfect. What about the bottom left? What did you all get there? Perfect, good. And the bottom right, how about that one? What do we have? Good, and it came from, good, the 5 and 15, perfect, perfect. So we agree that our partial products when we did this were 100, 50, 30, and 15. So what does that help a student do mentally? What mathematics actually occurred? So when you think about 15 times, there should be 13. 15 times 13, essentially what this does is it breaks it into a multiplication sentence of the sum of 10 and 5 times the sum of 10 and 3, which together makes 195. And if you are to add all your partial products together, 100 plus 50 plus 30 plus 15, we're going to get that 195. Now, if you're not familiar with elementary mathematics, you may be wondering, wow, that took a lot longer than just doing the standard algorithm. And in some cases, that's absolutely true. But what's important to know is that this strategy and this method that students are using will become something, and you'll see today, that they can use from their toolbox to help them when the mathematics gets more complex and not as easy to do through basic standard algorithms. But let's take a look at what that might look like. So when you think about that K-5 modeling to the high school algebra setting, the really cool part is that you have a story of units and a story of functions working together to give students a deeper understanding of mathematics. And one of my favorite parts that you'll love when you understand this piece is you'll notice that there are methods and tools that are consistent across the entire spectrum, and they are written into the curriculum in such a way that it becomes familiar for a student who engages in the entire process. It's very exciting. In our story of units, students get those foundational concepts that they need to help them do more complex work. When you get to story of functions, it provides that more complex work, such as multiplying polynomials. So let's take a look at how those connect. So a minute ago, we just went through the area model. And the area model is something that students in K-5 and our story of units use consistently. Now we're going to do something very similar with more complex math, but the verbiage is going to change, and that's important. It's going to be called the tabular method. And this is important, so you'll notice that the area model and the tabular method are going to work very similarly. But it's important to know why the name has changed. We use tabular method in later grades because negative numbers, which often aren't introduced till about 6th grade, are not as accurately depicted by length. And that length is what is represented when we look at that rectangular array. So we changed the name to tabular method, but the way it works is extremely similar to the area model. So let's look at something more complex. On that worksheet where you did part A, I would like you to look at part B. You're going to multiply the two binomials x plus 5 and x plus 3. So the first thing I want to do is I've already set up here a little bit of an example of going back to how we did the model earlier so we can practice a little bit more together. I've already set up your outer parameters for you of x positive 5 and x positive 3. I'd like you to take about 2 minutes, and I would like you to fill in the partial products based on this multiplication of binomials. And then we'll share out. Good, so it looks like everybody is finished. Let's take a look at this one together. You checked it with a partner, right? Yeah, okay, are you starting to see the connection here? This one's not as easy. We can't just do a standard algorithm. It's gonna be more complex. So hopefully you're already starting to see, oh, wow, these are some similar things that we can use with basic and more complex math. But let's look at what happens. So x you maybe mentioned was x squared, very good. Our next one is 5x, excellent. Next one, good, 3x. And our final one is excellent, excellent. So how does this work when we think about what we did with the area model versus this tabular method? Before, to find our total sum, our total answer, excuse me, we actually added all the partial products. But will that work when it's more complex? So let's think about it. So think for just a moment, what do you notice about the partial products along the diagonals? Just think for a minute, take a good look at it, and just think to yourself, what do you notice? Okay, what do you notice? Oh, good, good. So that's actually our first animation, so that works out well, excellent. You see an x squared by itself, x squared, very good. What about these corners, the diagonals here? What do you notice? Yeah, absolutely. They're like terms. You have a 5x and a 3x. And we know, we've taught students, and we know mathematically, what do we do with like terms? Right, we combine them. So that diagonal really is 8x. I have 8x's going on. I have the 5 times x and 3 times x, so I really have 8 times x. Excellent. And then someone mentioned there in the back, what did you say about the last one? Yeah, exactly. You have just the 15. Excellent. So we have the x squared, we have 8x, and we have 15. So when we just had whole numbers earlier, we added them all together to get our answer. Do you think that method's going to work here? Absolutely. So when we multiply those two binomials, it's the same as the product of the partial products. I'm sorry, the sum of the partial products. X squared plus 8x plus 15. And since they're not like terms, we just have x squared plus 8x plus 15. Now, I'd like to draw your attention to those arrows. A lot of people think, oh, I don't need to use the arrows. I would have taught it this way. But let me just show you something really cool from a sense of coherency. So right now, we're just talking about multiplying. We know that eventually students in high school are going to have to start undoing that and start going back into factoring. And that can be something that students really struggle with. And so when you think about how this is written, those arrows also help students in the beginning think through where, right now I'm trying to find the answer, I'm trying to find the actual product. But taking it back, those arrows, I like to show you what it can do. So if I want to just take a quick look here, that x squared, if I had to go backwards, I know that it would go here. I know my 8x would go here, and my 15 would go here. And that setup is really going to help students when they get to factoring, because then they'll just be working on filling in the missing partial products. But those are some really cool features of what you can do with this method. Very good. Awesome. So hopefully you saw some really cool connections there. So what I'd like you to do, we did that K-5 modeling with the high school algebra modeling. When you think about coherence, we've talked about what that means with the standards in the material. What coherence do you notice from part A to part B? Take about 30, 45 seconds. Let's think about it, and then we'll share out. Let's hear some of your thoughts. Okay, how about over here? What do you think? What's some coherence things you notice? Absolutely, absolutely, they sure do. Very good, very good. Let's hear some more. What over here? What do you think? Ah, yes, now we're cooking with grease. Yes, I love it. Very good, very good. So again, you already mentioned these, just some things to consider. You've already mentioned these, you're right. The same concepts of the rectangular array, but now they're using variables instead. And then you notice in the back, this is very catchy. I don't often see this in these presentations, but you caught on. Notice that the 10 and the 5, the 10 and the 3, it's a similar pattern to the x and the 5 and the x and the 3. So actually, if we were to replace that x with 10, we would have ended up with the same value as the 10, the 5, 10, the 3 from the original one that we did earlier. In this case, it's variable. We don't know the value, but if that variable happened to have a value of 10, we know what the answer would be. It would be that same 195 from earlier. Very good. So now we're going to take it to the final stage here. We've done the simple math. We've done the more complex math using the same method, but I kind of gave you a little bit of foreshadowing when I showed you the arrows. I'd like you to turn and talk with your partner. You have the trinomial x squared plus 2x minus 15. Now we're asking students to factor that and come up with the two binomials. Talk with your partner from what we've done so far on how you think you might begin to set this up. Because you've had a couple minutes to talk. I've heard some really good conversation, but I've heard some misconceptions on and off, so let's kind of walk through this a little bit together. I think some of you are really close to the right track, but once you see this, you're going to say, oh, absolutely. This is going to be great for you, great for students. So think about this. When you think about that trinomial, where would the terms appear? When we did the other one, we did the arrows coming from the diagonal. Where might these trinomial components and terms go into our tabular method? Where might they go? So let's start with, we have x squared plus 2x minus 15. So let's get those terms just broken apart at our x squared, our 2x, and our negative 15. So thinking about this model and this method, where would these terms go? How about yes, our x squared? Absolutely. I'm going to go in this diagonal. Where's that 2x going to go? What diagonal? Yeah, absolutely. It's going to go right there in that diagonal. Perfect. And how about the negative 15? Where will that go? Nice. Perfect. So now we know what diagonals are going to go. We can begin really piecing this together and doing some really awesome factoring from a conceptual perspective. So let's look at it. Think about this. We're going to work backwards to find our factor binomials. So because of what you just said and what we now know collectively as a group, which partial products can we actually fill in? And how do you know? So some things to consider. You said we can fill in the top left partial product with x squared. It's the only term with the unit of x squared. All right, we said that a minute ago with your diagonal, bring it down to the back. Excellent. So let's put it there. There's our first one. What else did we already say that we know we can place somewhere? Exactly, that negative 15. It's our only constant term. And that just leaves us with that 2x. And that's the beginning of the tricky part of factoring. But we have a really good method and model in place that's going to help both you and your students really understand how this works conceptually. So let's see what happens. Now we know we've got the x squared and the negative 15. What I'd like you to do, take a couple minutes with your elbow partner, and I'd like you to discuss how you would fill in these unknown pieces. So we don't know the missing partial products. We don't know the unknown terms of our ending binomials. What might we do to fill this in? How would we do this with this model? Let's take a couple minutes and let's talk through those together. Okay, so we've been talking for a few minutes with our partners. I've heard some great conversations, debate. I love this. Let's go through some of the things that I heard. So one of the things that I heard mentioned, I've already kind of put up here because I knew it would come up in conversation. Almost everyone I heard said the two unknown partial products, they got to add to be 2x. That's true, absolutely true. This is similar to our AC methods and other methods, diamond boxes, things we learned in the past. We know the two partial products must add up to be 2x. The other thing I heard people say was when you think about that 2x and how important that it is, you also said the unknown numbers in the blanks need to multiply to be negative 15. Since negative 15 represents the product of those two constants in the binomial. So we know we need the numbers to do both. So what were some numbers that you came up with? Okay. Good. Some of you did the S did, and we did it through a different method, but that's okay. You did. Okay, those are the numbers. But let's think through how a student's going to go through that. After thinking about those two parameters we set to fill in those partial products, we know that -3 times 5 gives us -15. That's our number. But we also know that +3 times -5 equals -15. So when a student's thinking through that, how do they know which one is which? Of those two options, we know that only -3x plus 5x will give us the 2x. Those are the only numbers that meet the parameters of both. So when we begin filling in our model, we've got our x squared and that -15 that we already knew was there. And now we've got our x minus 3, our x plus 5, and then our missing unknown partial products were 5x and -3x. And the really great part about this model and this method is students can go back and check their work through the process that they've already learned through multiplying binomials. We know that x and x is x squared, and we can check each piece to be sure that we know we have the correct binomials in this situation. So this concludes my excerpt number 4.